Hey guys, and welcome to our second lesson this week. So we're going to be talking about preparing solutions. Last time I likened concentration to lemonade, and I said that concentration is just how strong something is. So if you have something very concentrated, if you have very concentrated lemonade, it's going to taste very strong. Oftentimes you might want to change a concentration. You might want to make something dilute. You might want to dilute something. Same idea with lemonade. So if you've ever made frozen lemonade before or frozen orange juice before, we start with what's called concentrate. So that's that kind of like frozen, really sugary, really sour thing that you pull out of your freezer. You don't want to drink just that. So in order to decrease the concentration or decrease that really pungent lemonade flavor, you want to go ahead and you want to add water. That's the active dilution. In chemistry, we're a little bit more precise than just adding in water though. One thing we have to be careful with is being very precise. We have specialized equipment and we use what's called a volumetric flask. So these flasks are come in all different sizes. In my class, I have 50 mil, I have 100 mil, I have 250 mil. And what they are is they just have a set line. So the line might be here, and that's how much you want to fill in order to measure. So for example, on a 50 mil flask, I'm going to have a set line and I have to fill to that set line in order for it to be 50 mils. Now I understand what you're thinking. Why would I use a flask that can only measure to one height when I can use a graduated cylinder that I can measure to whatever height that I want? And the answer is accuracy. So a volumetric flask is about 0.1 milliliter plus or minus of accuracy. You want to be as precise as possible. So when you're making a dilution, you always want to use a volumetric flask. You don't want to use a graduated cylinder. When you're going through a couple terms we need to know about, the term we're going to talk about today is going to be a standard solution. So what a standard solution is it's a solution with a known concentration. It's a concentration that we can be confident that that solution has that concentration. There's two ways that we can make standard concentrations. One is by taking something from a solid form. So I do this with sodium hydroxide all the time. It's by taking solid sodium hydroxide pellets, adding water to it, and diluting it to form a liquid. The second way that I can form a standard solution is by diluting a water. So you'll see this with hydrochloric acid. You might see this with acetic acid as well too, or just table vinegar. So those often come as liquids, and to dilute it, I want to add more liquid to make it less concentrated. A couple steps for preparing a standard solution. So normally I would walk you through this in the chem lab. I'm not in my chem lab, so we are going to go through and we are going to improvise based off some of the stuff that I have here. Okay, so let's say that I was trying to make a solution of sodium hydroxide. We're going to pretend that sodium hydroxide is these blue pellets here. Really, all this is this is just like liquid plant food that I've actually been using in my tomatoes. So we've got a solid here. So first thing that you want to do is you want to be as specific as possible. So in a chem lab, you would use a balance to go through and to mass this to actually 2 decibels. Then we want to go ahead and we want to dissolve a small amount of this into our distilled water. So to do this, you would always want to start with a small measuring vessel. Again, you would be using a small volumetric flask in class. I don't have that, so I'm using my small measuring cup. So what you'd want to do is you would want to add a little bit of water. And by adding a little bit of water, what's going to happen is this substance is going to dissolve. You would then want to take this and pour it into your larger volumetric flask. So again, not a volumetric flask, but you can kind of see the size difference here. So you would want to go ahead and pour this into my large volumetric flask. Now, the reason that I use blue is because what you are going to notice is that this is not perfect. Look at all this blue stuff that's left over in my smaller container, right? So I want to make sure I was very specific when I measured this amount. So I want to make sure I get this into here. Otherwise, my concentration is not going to be correct. So what I'd want to do is I would want to use a wash bottle and I would want to continue to dissolve and to add until I essentially have no blue liquid left. Once I've done that, what I want to do is I want to go ahead and fill up my volumetric flask to the fill line. So let's say that the fill line is here. I would go to make sure that I was flush on, and I would fill it up to the fill line. A lot of the times with concentration, you can actually easily see when you're diluting something, because notice that this blue is already a much lighter blue than what we were just using before. So that's exactly how you would go through and you would create a solution in a lab. You want to make sure that the bottom part of the meniscus, so if you've ever looked at a fluid right on, going up a graduated cylinder, a meniscus is, it looks like this. Let's draw this. A meniscus is going to look like this. So the idea is that the water is going to stick to the sides of the glass. So the edges of the water are going to seem higher than the lowest part of the water. So it's not going to be a flat line. It's going to be almost like a bubble. When you're doing this, you want to make sure that the bottom part of the meniscus touches the line that you're trying to measure to. So let's say you're trying to measure to this line here. You want to have the bottom part of the meniscus, not the top part of the meniscus, touch these sides. That's how you know you're exactly accurate. You then want to make sure that you transfer to a clean container once you've made your solution. We don't store things in volumetric flasks, we store them in bottles, and you'd want to go through and put your WHMIS label on. When you're diluting a standard solution, sometimes you're required to have several of the same chemical of different concentrations. So you might want to go through and create something that's called a stock solution. For example, when hydrochloric acid comes into our lab, it actually comes in at 12 molar. However, in grade 11, you always use it at 1 molar, and in grade 9, you actually use 0.1 molar, just to be safe. So I actually will go through and I'll dilute our stock solution that's downstairs to the proper concentration that you might need. By doing that, I'm forming a compound that has a lower solution. So when you're diluting, it's implied that you're going from a higher concentration, 12 molar, to a lower concentration, 1 molar. In order to calculate this, and this is actually a very useful calculation, I probably do this calculation maybe 50 times a year when I'm setting up our labs, we're going to be using this formula here. So notice that we've got two different sets of letters. We've got C and we've got V. C is going to stand for concentration and V is going to stand for volume. Notice that we also have the letters I and F. I stands for initial and F stands for final. So C is going to be our initial concentration. That's the stock solution. That's the known concentration. So that's my 12 molar hydrochloric acid. V is going to be the initial volume of the solution that I need to use. F is going to be the final concentration that I'm trying to get to. So let's say I'm trying to make 1 molar solution. So CF, concentration final, would be 1. And VF is how much you're producing. So you might need to calculate different numbers of these. I usually typically have to calculate VI. So normally in a lab, I know the concentration that I'm starting with, I know the concentration I'm ending with, and I know how much acid I need to have one lab be successful. So let's say we have 20 students, each student needs 1 mil of acid. I would need to make 20 mils of acid. So usually I'll know CF, I'll know VF, I'll know CI, and typically we're going to be looking for VI. But the idea is with this formula, as long as you know your 3 variables, you can always calculate your fourth. So let's go through and let's look at an example. This is actually an example of a sample calculation I actually do with my grade 12 class in their esters lab. So how much 18 molar? So remember that big capital M molar stands for moles per liter. That's the concentration. Sulfuric acid solution is required in the preparation of 50 mils of 2.0 molar H2SO4. So the hardest part of this question is actually going through and figuring out what concentration and what volume go together. So I'm going to help you dissect that right now. How much 18 molar sulfuric acid solution is required in the preparation for 50 mils of 2 molar H2SO4. So it's implied that that concentration and that volume are actually going to go together, and the other concentration is on its own. The second part that's challenging is to figure out whether you're talking about the initial concentration, or the final concentration. Remember, in a dilution, your final concentration is always going to be lower. So since 2 is lower than 18, then we know that this must be my final concentration. Therefore, this must be my final volume, because those two values are going to go together. And this must mean that this is my initial concentration. So I must be looking for my initial volume. So let's go ahead and let's record these in a nice, neat manner. So I've got my initial concentration, my final concentration, and my final volume. And let's remind ourselves of the formula. So my formula is CIVI equals CFVF. The fact that those C's and V's are beside each other, come back, just implies that you're multiplying. So you're multiplying these values and you're multiplying these values here. Sometimes, depending on the formula, you might actually see this listed as C1, V1, C2, V2. It's the exact same idea. Next up, all we want to do is we want to isolate for VI. That's what we're looking for. So in order to get VI by itself, we want to get rid of CI. Since we're multiplying by CI on the left-hand side, that means we want to divide by CI on the right-hand side. Last thing we're set to do is go ahead and plug in our numbers. Be very careful of units here, because this can get a little bit tricky. So we've got 2 molar, or moles per liter, times 50 milliliters, divided by 18 molar, and you are going to be left with 5.6 milliliters. So since this value was given to you in milliliters, you're going to report your final answer in milliliters. Sometimes it's going to be given to you in liters. Sometimes it might be given to you in a different volume, depending on how large or how small your quantity is. So be very careful of what unit you're putting in, because that's the unit that's going to come out. So therefore, your final solution is going to be 50 mils, and you need to use 5.6 mils of the initial stock solution. This is a new question. This is good. Okay, so we're going to go through a new question. Sorry, guys. So if my final solution is going to be 50 mils, and I need to use 5.6 mils of the initial stock solution, how much water do I need to add to the stock solution to make the final dilute solution? So this is an extension question of what we just did. So let's look and see how we would go ahead and set that up. So the volume of water that you need to add is going to be your final volume minus your initial volume. So it's how much water you're going to have to add in order to dilute it. So let's remind ourselves that we're trying to end with 50 mils. So we're trying to end at the 50 mil line. And we started with 5.6 mils of liquid. So the question is asking, how much water do you need to add to 5.6 mils to get to 50? And you're going to find that you need to add 4.4 milliliters. So again, when you're using a volumetric flask, you don't really have to worry about that. You're just going to be filling to the line that you see, but it's nice to know how to do this calculation. Okay, one thing that we have to be careful with, and it's great to talk about safety as well too. Every time that I am diluting acids and water, you always want to make sure that you are going to add the acid to the water. The reason that you want to do that is twofold. If you have a giant vat of very concentrated acid and you pour water into it, what's going to happen is that concentrated acid is going to splash out, and there's a good chance that you are going to burn yourself. The second reason that I'll understand a little bit more with math in grade 12 is the idea that when you are actually adding acid and water together, it releases an enormous amount of heat. So there's one lab that I actually have to make 8 liters of acid. So you'll see me like with giant volumetric flasks walking around. The idea is the more water that's present, the more water will actually absorb that heat. So if I slowly add acid to water, I'm not going to crack my glassware. If I have a bunch of acid and I add just just a little bit of water, there's not enough water to absorb that heat, and my glassware could actually crack and explode, and I've got really concentrated acid that'll spill out everywhere. So you always want to make sure that you add the acid to the water, not the other way around, and you want to make sure that you go really slow to make sure it doesn't get too hot. Just a quick note about units. I touched on this a little bit. It actually doesn't matter what units you are using for volume. So remember yesterday, we were always converting to liters. Notice in that question, we didn't have to convert to liters. We just reported our answer in milliliters. What happens is that VI and VF have to be in the same units. So if you're using milliliters, you have to report in milliliters. If the question is asking you to solve for VF and you were given VI in milliliters, just leave it in milliliters. If VI is given in liters, just leave it in liters and you're going to report in liters. A couple other notes that VI is always going to be less than VF. So in order to go ahead and dilute, you saw me with the blue before, if I'm diluting, I'm adding water. So I'm always going to end up with more solution than I started with. With CF and CI, CF is always going to be less than CI. So by adding water, I'm diluting, I'm decreasing that concentration. So I'm always going to start strong and end weak. That's the whole point of me diluting. All right, that's it. That's dilution. So try these homework questions. They're going to be great practice. Join us tomorrow, and we're going to look at a new concept. Have a good day. See you later.